Gauss's law of electric fields states that the total electric flux through a closed surface is directly proportional to the total charge enclosed within that surface. Taking a look at Gauss's law in integral form, we first have an electric field E. This is a vector field that points away from positive charges and towards negative charges. The left-hand side of the equation represents electric flux, which is a measure of how much electric field passes through a given area. Mathematically, the surface integral sums up the electric field contributions at all points on the closed Gaussian surface. dA is a differential area element on the closed surface that is normal to that surface. If the electric field line is exactly normal to the surface, the dot product E dot dA is just the magnitude of the field multiplied by the area. This is because the angle between dA and the field is 0 degrees. So what if our E field goes through our surface at an angle? Remember that we can split up any vector into a tangential and normal component. If the electric field through the surface is at an angle to the surface, only the normal component of the vector field contributes to the electric flux, because the dot product of two orthogonal vectors is 0. You can also see intuitively that the tangential component of the vector is not contributing to the flux at all. So the surface integral adds up the contributions of the electric field over every small dA area on the surface. The dot product ensures that we only add the component of the electric field that is normal or perpendicular to the surface. This integral gives us the total electric flux through our closed surface, and states that this value is equal to the total charge enclosed within that surface. Also, as a quick note, epsilon naught is a constant known as the permittivity of free space. It essentially sets the scale for how electric fields interact with charge in free space, and is a necessary addition in this equation. Now, you've probably also seen Gauss's law written in a compact point form. Using Gauss's divergence theorem from vector calculus, we can replace the surface integral on the left-hand side with a volume integral of the divergence of the electric field. We can also express Q as the volume integral of the charge density ρ. We are then left with Gauss's law in point form, which states that the divergence of the electric field is equal to the charge density. The divergence of the electric field at some xyz point is a measure of how much the electric field diverges, or spreads out from that point. So if the divergence is positive, we have a positive charge density, and we know that the electric field is spreading out from that location. If the divergence is negative, we have a negative charge density, and we know that there's a sink where the electric field is converging. So what if the divergence of E is 0? If the divergence of the field is equal to 0, that means there's either no charge or the same amount of charge coming in is also flowing out. Essentially, Gauss's law gives us a way to mathematically understand how charge relates to an electric field. It helps explain that electric fields are associated with positive charges as sources and negative charges as sinks. This gives us mathematical intuition for electric charge as well as electric fields.